Okay, so graphs of basic functions, we're going to start with sine and cos. Notice how there's an empty part there. I'm going to leave that for you, right? Those are for exact values. Again, that's practice of knowing what your sine and cosine and tan values are, okay? Exact values. What we've given you is the decimal form of those values. And so we want to graph y equals sine theta and y equals cos theta, and we'll get into tangent as well. Okay, so notice the axes, these are in radians. Okay, notice the grid markings. So these are things that you will want to notice as we go through trig. We're going to be doing transformations, a lot of trig functions. So you want to look at the grid markings, count them up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 grid markings for each pi unit. Okay? So pi over 6, in terms of grid markings, that's the same as 2 pi over 12. Right? So you'd want to look for 2 grid markings over. Pi over 4 is the same as 3 pi over 12. Okay, so your unit point's going to be 3 grid markings over. Pi over 3 is the same as 4 pi over 12. Okay, pi over 2 is the same as 6 pi over 12. 2 pi over 3, so you can do that. You'll get the pattern of it as we go through. For the first graph, we're only looking at the sine values. Okay, so that's saying when theta is 0, the sine value is 0. That's your x-intercept and your y-intercept. Then the next one, when theta is pi over 6, which is 2 pi over 12, so 2 grid markings, the sine value is 0.5. So now look at your axes this way. This whole, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 grid units for each whole unit. So half a unit would be 5 grid markings. So 1, 2, 3, 4, 5. Then for 3 grid markings, 0.71. So you're going to estimate a little bit. 4 grid markings is 0.87. Again, you're estimating a little bit. And for pi over 2, which is 6 grid markings, it's at 1. Then take a look what happens. These values now decrease with the same value. So we've got up to the top here, and then we can go back down. Okay, so I call this like a mountain, and then your next part of it will be a valley. Okay. So here, I'm just going to multiply by 2, so that's 14 grid markings, or 1 pi over 6 half pi, which is 2 grid markings. And now you'll notice that the sine value is negative 0.5. So 2, 4, there. So same values, opposite in sign now. 3 grid markings is for the next 5 pi over 4, because that's 15, and that's negative 0.71. Then the next is negative 0.87, and then we go skip a grid marking and go to negative 1. It's symmetrical, so this mountain is symmetrical from that maximum. This valley is symmetrical from the minimum.
So this is a double reflection about the x-intercept. Like as in the reflected to both axes.
Because remember, these are all based on reference angles, right? So unit circle, all the triangles are the same, they're just in a different location. And that's what we've used here as special angles. There's obviously values in between. That's why we're joining it with a curve, but we're doing the special angles.
I guess you could also kind of think about it as like a quadratic that doesn't extend out, and then you reflect it about 4 axes.
Yeah, it's not in the shape of an exact quadratic, but it's
more of like a hyperbola shape.
Yeah, it's a sinusoidal curve,
Yeah.
so it has its own.
Has its own little.
So then going to the left, notice on your chart, you don't have negative values. But think about where they are. And basically from here, this is going to be another value. So it's going to be exactly the same as this. So notice 2 grid markings was half a unit, 5 grid markings down. So 2 this way, and 1, 2, 3, 4, 5 down. 3 grid markings was 0.71. So 3 grid markings will be 0.71. 4 grid markings will be 0.87. 6 grid markings will be -1. Okay, so use your symmetry.
Oh, I never seen a relationship.
2, 1, 2, 3, 4, 5.
Well, we have to like plot these exact stuff. Well, you're not going to be able to draw one of these out. You just plot the calculator.
Well, you do have to know how to draw.
Yeah.
You're going to be doing transformations, so.
How many points would we need?
2 cycles worth, so.
That.
Or one, for sure 1 cycle, maybe 2 sometimes. Okay, put arrows on the end. This goes to infinity. Okay, properties to look at that we're going to summarize. Okay, that it is, first of all, the domain is all real numbers. Okay, those arrows go on forever. The sinusoidal covers sine and cosine graphs. They're actually exactly the same graph, just in a different location. They're translations of each other horizontally. Base graph, max is always 1, minimum value is always -1. For sine, it goes through the origin. Okay, so that's really important. The difference between sine and cosine is the location, as I mentioned, but sine goes through the origin. And I always think about it, sine goes up and to the right from the origin. Okay, so it's got a hill, then a valley. Cosine, okay, I'm just quickly going to do cosine. I'm going to get you to do cosine on your own. But cosine starts at the top. If you look at your table of values, when theta is 0, cosine is 1. Okay? And then it has so basically that's the height of the mountain. So where it starts the valley is at pi over 2. So here. So you don't have to do this right now. I'm going to get you to do it on your own time because you have done this last year, whether you remember or not, but you have. So just give me a sec to get these.
This is sine, cosine.
Okay, so I'm just going to show one cycle, but that's cosine, same shape. Now, the graph at for an x value or a theta value of 0, it starts at the maximum and goes down, okay, down and to the right. So it splits the mountain in half there, or the y-axis. The length of a complete cycle, so this is a complete cycle, one mountain, one valley. However it's split up, that length is 2 pi, or 360 degrees. Okay? So that's at negative pi over 2, this is 2 pi over 2. So that's 2 pi. That we call the period of the sinusoidal function. The length of a complete cycle, not just of a mountain, but of a mountain and a valley. Okay, that's called the period. This line here, that basically cuts it from mountains and valleys is called the midline. Okay, then midline value, in this case would be 0. Sometimes we call it the median line. And then the amplitude is the distance from that midline to its max or to the min. It should be the same. Otherwise, it's not a transformation of a sine function. Okay, so you may have already talked about that in physics when we were talking about sine waves for sound, that kind of thing. Probably you talked about it. Okay, so similarities and differences. Same shape, but translations of each other. Okay, so from that, so same domain and range. Max and min values. The actual max and min points are different, but the max and min values are the same. The domain and range, max and min values, midline, amplitude, all of those are the same. It's just the location. Midline amplitude. Okay, so a function is said to be periodic if it repeats itself over regular intervals of its domain. So these are periodic. Got mountain and valley. So this says same domain and range, max and min values, midline and amplitude. All the same. As I just mentioned, the period is the length of that cycle, okay, that interval that does repeat. And so that's going to be 2 pi, or 360 degrees. Midline amplitude. Okay, so just in terms of data, and maybe you've done this more in science class, you've collected data. So sinusoidal data is periodic data. It doesn't have to be in the shape of this curve, but it's it's a wave pattern for sinusoidal. So periodic can have shapes like squares that repeat, that kind of thing. But sinusoidal has the shape of a sine graph, cosine graph. Okay, so this is yes. And as I mentioned, domain is all real numbers. Unless you restrict it for some reason. But any x value, or this theta equals theta. Okay, looking at this graph, the max is 1, the minimum value is -1. So the range from -1 to +1. The amplitude is half the vertical distance between the minimum and maximum points. Okay, the amplitude for the sine and cosine graphs is just 1 for these base graphs. Okay, so if I'm looking at a graph, I just draw the midline and I look at that distance from the max to the midline. Or, as it kind of says here, it's the half, so you can take half of the max minus the min. You want a formula, but that's up to you. Median value is the value halfway between the max and min. That's that line that cuts the mountains from the valleys, the value of it. So in these graphs, it's 0, because that is the x-axis, so y equals 0. Right? That's your median value. And the midline is the actual line that you graphed it. Okay, so the equation of the midline is y equals 0. Okay, so now let's go back to look at our sine graph. It says the general expression for the theta intercepts. So theta will equal, so what are those intercepts? I'm going to go this way. Okay, so here's sine. So where are they? -2 pi, -pi, 0, pi, 2 pi. What do you think the next one is? 3 pi, 4 pi. So what multiples? How could we say that a lot easier?
Phi, like n phi plus, or n phi where n can be any integer except 0.
Yep, it can be.
Oh, no, okay, you're right. We're not saying cosine.
Yeah, it's just a multiple of pi. So sine is really easy. The theta intercepts, in this case theta, sometimes we use x, but they are multiples of pi. So n pi or pi n doesn't really matter. Again, we had this conversation in math office. What do we do now? I'm putting in pi. I think I used to put pi n. I don't know. Anyway, and then for IB, Z is integers.
You can also say like plus or minus n is natural number.
Yeah.
Or
You can go plus or minus n, 5, where it's whole numbers. Then cos here, a little bit different. So this is pi over 2. This is 3 pi over 2. Okay. This is negative pi over 2. So, if I said it was a multiple of pi over 2, using integers, what would happen? Would that work?
no,
So if I said pi, okay. So pi over 2, if I said multiple of that times n, and if n was 1, that's good. Okay? If n is 2, what happens? You get pi. So we get 2 min. Okay? So, what we want to do here is, well, there's a couple of different ways of doing it, but I always look for the first positive, and this will help us when we're solving harder equations as well. So first positive is pi over 2, okay? To get the next one, what am I adding? 1 pi, right? So I'm adding pi to get that one. What do I add to get the next one? Another pi, so 2 pi, and then 3 pi, and then 4 pi. So again, pi n or n pi, right? I'm adding that. Similarly, if n was a negative, so if I subtract pi, do I get the right one? Yeah. So I can use this where n is an integer, okay? Or I guess you could use plus or minus pi over 2. Plus or minus, and then pi over 2 plus pi n, where n is a positive. So,
no, because that doesn't actually give you everything. That's still only give you positive.
With the plus or minus.
Oh, with the plus or minus.
Yeah. I would just keep it like this, personally. I don't use the plus or minus, but there's more than one way of stating that. So what I do is I always look at the first positive, write it down, and then think about what I keep adding, because it's going to be, it's periodic, right? It's going to be the same amount every time. What is that amount? In this case, it's pi each time. So multiples of pi.
You can also say like n plus 1/2 brackets 5, like n plus 1/2 5. Because you just factor out 5.
I guess. Yeah, I guess. But we never really show in factor form, for sure. So I've never done that or seen it on the online for that. So I'm going to keep it to pi over 2 plus n pi, where n is an integer. Okay. Okay, y-intercept of sine is 0. Remember, it goes through the origin, right? Y-intercept of cos, though, is 1. Okay, so properties of sinusoidals. You're not given the equation, so you can't actually, you can tell from an equation, but you're not given it. You're just given the graph. I'm just going to maximize this again a little bit. So what I do is I draw the midline. So take a red. So my maximum there is 12. My minimum is 2. So halfway in between is the average. All of you know how to get your average. You do it when you get a test, right? Add them and divide by however many. So add 12 and 2 is 14 divided by 2 is 7. Sometimes you don't even, you can tell really easily where it is. So I draw a line across. That's your midline. So my equation of the midline is y equals 7. If we ask you for the equation and you just say 7, you get it wrong. 7 is not an equation. Okay, so look for that word. So in this case, it's easy. Amplitude is that distance there. So 12 minus 7 is 5. If you want a formula, then remember what it was defined in the notes. Your maximum minus your minimum divided by 2. Maximum minus minimum gets you the entire height of the whole thing divided by 2. Amplitude is never negative. It's an actual distance. In an equation, you might end up seeing it when we talk about equations. You'll look for the amplitude. You might have a negative in front, but that just tells you the direction of opening, basically. Has it been reflected or not? Okay. Then the period. So you can look for the same point in two cycles, right? The beginning of a cycle and the end of it. So you can either look, for example, from here to here. Look at these x values, okay, and subtract them. You could look from here, so this midline to where it starts again there, and subtract those. If you have enough grid paper, start where it's at 0. So this point here, where does that point repeat? It repeats over here. So then you just know right away it is 2 pi over 3. Right, for a complete cycle. So this is not the base graph. It's had transformations done to it, and that's why the period is not 2 pi. If you say did from here to here, that's 7 pi over 12 minus negative pi over 12, which is like adding it. So 7 plus 1 is 8 pi over 12, which is 2 pi over 3. Okay, same. There's just a summary of what we've talked about. Cycle is basically part of the graph that is repeating. Periodic data that contains cycles, which repeats. Sinusoidal data is periodic, whose graph can be represented by that wave pattern. Length period is the length of the shortest interval that repeats. Median, halfway in between. Midline is the actual line, so it has an equation. Amplitude, half the distance. So we talked about that. I showed you that. So those are some properties. And then there's actually for you a diagram, it's actually on my second one. Okay? So that's what I have to do. Draw a midline, draw the amplitude, count it up, and then find a nice cycle. Okay? So here, there's a mountain, there's a valley, so you know for sure that that's a complete cycle. Okay? Or if your graph is nice enough, I don't know the exact value there, but if I follow it through, it's going to be symmetrical over here. And again, kind of depends on your grid line. Can you tell what it is? So this, I can't quite tell. And notice how these values are actual integers there. So it's not in terms of pi. Okay, so I won't be able to tell exactly what it said. Okay, so we're not going to get through everything, but we're quickly going to look at tan. So at least we've done the primary ratio. So turn over on the left side, and then we'll just do the left side and be done for today. Okay, so use the table of values on the first page to graph y equals tan theta on the grid below. You'll have to supplement the values in the table so you can draw an accurate graph. Yeah, because we don't have every single thing in our table of values. You are going to have to kind of flip back a little bit, but we've done those calculations for you. Take a look at the scale. So again, 12 grid markings for each 5. But here, this goes up to 10. So each one of these is 1 unit. Okay, so it's different from sine. And that's because tan, you can't have large values for tan, right? There's no max on tan values. Think about where, on your chart, think about where tan value is undefined. So if you take a look at your chart there, this infinity symbol means it's undefined there. So tan is undefined at pi over 2 because your y value is 1 divided by x value is 0. You cannot divide by 0. So it's undefined at pi over 2. It's undefined at pi. Oh, not pi, sorry. 3 pi over 2. Okay. So if it's undefined, we're going to graph an asymptote. And they're the same distance apart. So in our table of values, we have one at pi over 2 and 3 pi over 2. So that means the distance between them is pi units. So we've got to have in the same direction.
It's like a bunch of repeating, well, it's kind of like a bunch of repeating units.
Yes.
Well, not in that sense.
So just like sine, x and y intercepts are 0. It goes through the origin. And that's because sine is 0 at 0. And tan is sine over cos, or y over x. Pi over 6 is 2 grid markings, is 0.58. Again, it's small, right? Each of these is 1 unit, so you're really just estimating best you can there. Once you've got 2 cycles, just leave it. I'm not going to spend the time going through all. They're all going to be the same. Okay? So see if you can get 2. Obviously, your chart, the table of values didn't have these ones. I put them in myself based on the fact that they're all going to be just negative of the positive, because that's in the 4th quadrant with those reference angles, and tan is negative. Okay, so in terms of graphing tan graphs, here are my hints. First of all, remember, 0, 0 goes through the origin. looks like, kind of like a cubit, right? Going through the origin, so it kind of zigzags. But what are the nice points? That's a nice point, and that's halfway in between the asymptotes. So if I told you there's asymptotes at x equals 10 and x equals 20, then you know that what we call a point of inflection is halfway in between at 15. Right? It doesn't matter what the unit is. It's halfway in between the asymptotes. Then take a look at this nice point. This has a y value of 1. Well, where is the x value, or theta, it doesn't really matter, located? It's located halfway between the point of inflection and the asymptote. Okay, so 1 unit. So you know how kind of with parabolas, we go 1 unit over is 1 up, 2 units over is 4 up, unless you do a transformation. Well, now, from the point of inflection, halfway between that and the asymptote is 1 up. To the left here, halfway is 1 down. Okay? And then really, like, in terms of graphing it, we're not going to ask for too much more, as long as you can not make it like straight lines. Make it curve through those 3 points in the cycle. Okay? With the asymptotes approaching it. Don't be lazy and put it crossing over. So again, if I have these asymptotes, halfway in between is here. That's on, it's not really called a midline, right? But it kind of is, right? It's where it splits that graph into parts that aren't, it's not symmetrical, but it's
a reflection about
it's a reflection about each of these. So it's not called a midline, but it essentially is like a midline. So halfway in between that point of inflection and the asymptote, okay, the x value there, 1 up is another point. Halfway the other direction, 1 down is another point. Then you do your best curve that you can. The arrows on the end. Okay. So that's a tan graph. I'm going to just put it into dual here. Okay. So what are some properties? Is it periodic? I haven't drawn all of them, but does it repeat? Yeah. So yes, it's periodic. Okay. Now, what is the period? So for sine and cos, it was 2 pi. What do you think it is? This one? None? Pi. It's half as much. Okay? It's the distance between these asymptotes, because that's the part that repeats. So for tan, the period is pi. The sine and cos, the period is 2 pi. Tan is pi. Memorize it. Why is the graph of tan theta not a sinusoidal function? Well, does it look like a wave? That's really what we did. It is periodic, but it's not sinusoidal because it's not a wave. It doesn't go up and come back down again. So it doesn't have a wave pattern. Okay, so given that, does it have an amplitude? No. So there's no max or min point, so there's no way we can have an amplitude. So if the arrows are going on those ends, distal means when we're talking about polynomial qubits, what's the range? So infinite, so it's all real numbers.
Do you ever take the limit of that function, like as x, or whenever, I guess what do you call x here, approaches the asymptote, it's plus or minus infinity. Depending on which direction you're approaching the asymptote.
The graph of y equals tan theta has vertical asymptotes at theta values where cos of theta is what? So think about, remember, so tan of theta is y over x. when we do that on our unit circle, our y value is sine and our x value is cos. So where our asymptotes are when our cos values are 0, right? So where cos of theta equals 0. So back just a little while ago, we found where cos of theta had its x and its theta intersects. Right, where it crossed the theta axis, the horizontal axis. That means that's when the value is 0, right? So the vertical asymptotes will be, vertical is, we have to actually have the equation. In this case, we're using theta. So the equation of these, the vertical asymptotes, is the same as where cos is 0, right? Those intercepts. You can see there's pi over 2 plus pi minus pi minus pi to pi. So those are the equations of the asymptotes. For the domain then, it's everything except those values. So now we put the not equal to pi over 2 plus n pi, and it's a set of reals. And theta is, it gets messy here, theta is a real number.
Well, can you also put x, or should we use theta?
In this case, because we called it theta, we should.
Use it. Well, that's pretty, hey, at least we don't have to write it with, interval notation.
Yeah, you can't use interval notation really on this. Okay, now the theta intersects of these graphs, that's really where sine is 0, right? And so that is 0, pi, 2 pi, etc. Those were the intercepts that we did for sine. So that one's a little bit easier. So theta intersects, theta equals n pi.
So this is, I mean, it's not exactly, because it's not technically a rational function, but since it's in, like, if we look at it in a fraction form, once again, the asymptotes are where the denominator is 0, and the x-intercepts are where the numerator is 0.
Yeah, we're going to have to find descriptions for this function for sure. Okay, and then the y-intercept of tan theta is 0. Okay. We are going to leave it there, and we'll do reciprocals tomorrow. Okay.